Hello, Honors Physics students. I need you to have your notes in front of you because you're going to be taking notes while you watch this video. This is the official introduction to our next topic. This is packet number 6 called Impulse and Momentum. And in this video, I'll be introducing you to some of the definitions, equations, and units for the new terms in this topic. So I normally start this topic by asking you a very simple question. What's the biggest equation of the year? And hopefully you would all respond. Sigma F equals ma. So let's start with that. Here we go. Sigma F equals ma. And the next question I would ask you would be, what was our original definition for acceleration? The original equation we had for acceleration. So some of you may say it was delta v over t. Others may say it was vf minus v naught over time. Either way, you got the right idea. So here we go. We're going to write that acceleration equation, delta v over t. Now, notice I've already changed it a little bit. Instead of writing t, I've written delta t. That's to highlight the idea that it's not just a moment in time, but there's an elapsed time through which the velocity changes. So it's a little more appropriate to write as a delta t, a change in time. And all we're going to do is we're going to combine equations. I'm going to drop this equation for acceleration right in here, where acceleration is in sigma f equals ma. So let's combine those equations. Here we go. And you're writing all this down in your notes. So here we go. Sigma f equals m times delta v over delta t. Nothing fancy. Now I'm just going to play around with the algebra in a similar way to how we had done in working energy when we put together some equations and derived some new terms. First thing I'm going to do is just move delta t over to the left-hand side. So there it is. Sigma f delta t equals m delta v. Nothing fancy there. On the right-hand side, we're just going to expand out the delta v. We know delta is always final minus initial, so let's replace that. So we got sigma f delta t equals m times the quantity, vf minus v naught. Then all we're going to do is multiply through the m, distribute it to both those velocity terms. So here we go. Sigma f delta t equals mv final minus mv naught. We notice that we have the same quantity twice. This is mass times velocity. This is mass times velocity. It just happens to be final minus initial. So we can say anytime we do a final minus initial, we can just replace that with a delta. So let's do that. So sigma f delta t equals the change in the quantity mv. We're going to stop here with the algebra because we're going to define one side of this equation as one new term and the other side of the equation as the other new term. So I'm just going to rewrite it here with a little more space in between. You don't have to rewrite it. It's up to you how you want to do in your notes. But one side of this equation will be one new term, the other side will be the other new term. You might even be able to guess what those two new terms are. Go ahead and give it a guess. If you said impulse momentum, you are correct. You should have, right? You're smart kids, and of course the title here is impulse and momentum. Those are our two new terms, so here we go. The left-hand side of this new equation is that we're going to call the net impulse, because it involves the net force. The right-hand side of the equation we're going to call the change momentum, because it's the change in some quantity, and this new term inside here is what we're going to call momentum. Alright, so we have two new terms, impulse, momentum. Let's start with some definitions here, first starting with impulse. Alright, so you've probably heard the word impulse before in everyday life, and normally in class I'd ask you to give me an example of what an impulse is, what it means to have an impulse. So just think that through for a second. Okay, so I'm sure you've heard it before. Most students say it's like a sudden urge to do something. So let me give you an example. Let's say you're at the grocery store, you're helping your parents shop at the grocery store, and they give you a budget, and they give you a list of things to get, and you go around putting things in the carts. And if you ever have those scanners, when you scan the item, it'll already add it up for you. So this is great. So you're doing that, and you're checking things off the list, and you're done with the shopping trip. You checked everything off your list, and you check your scanner. You were under budget. Things are going great. All right, so there you go. Over to the line. You're waiting in line to pay for everything. And as you're waiting, you're passing by these racks. On one side of you, there's a rack of glossy magazines, and glossy magazines weren't on the list. On the other side of you, there's a rack of discounted Halloween candy, and Halloween candy was not on the list. And yet, all of a sudden, you have this urge, this impulse. You have to know what the Kardashians are doing, and you have to have some Hershey's Kisses when you do it, and so you grab these things off the cart and off the rack and put them in your cart, and all of a sudden, you're over budget. These things are called impulse buys because they grab your attention, and all of a sudden, you make a sudden change in what you're doing on an impulse. You decide to buy these things. Okay, so that's how we use it in everyday language. It turns out that there's almost no relation to how we use it in physics. In physics, we call an impulse the effects of a force extended in time. All right, if you look at the equation, there's force, there's time. It's the effects of a force extended in time. Now, a lot of times, the forces we use act for a very short amount of time. So in this case, it's like an impulse, a sudden change in what you're doing. But sometimes the times are longer, so it's not really related to how we use impulse in everyday language. Okay. All right, we're going to need a symbol to use for impulse. And in class, I would ask you what symbol you might want to use. And most students say, we'll use I. That makes perfect sense. I for impulse. And I say, yes, that does make perfect sense. Except we're not going to do that. We're actually going to reserve I for something else later on in the year. So we're not going to use I. So I take other guesses, but no matter how many times I ask students to guess, unless you've seen it before, you're not going to guess, because we're going to use capital J for impulse. I know. It doesn't make any sense. There's no good reason why we use capital J. Honestly, I think we just ran out of letters, so we'll use capital J. There's our symbol. All right, now we get to the equation for impulse, which comes directly from this equation, except this is for net impulse. We're just going to get rid of the sigma, so we'll say J equals F delta T. Let's consider the vector and scalar nature of these terms. We've got force, and of course force is a vector, and we got time. Time is a scalar. This means that impulse is a vector. So we can put the vector arrows over the J's there, and now we can box in our new equation, J equals F delta T. Okay, let's define the terms in this. J stands for the impulse from a single force. This is the equation we use when there's only one force acting on the object, or we only care about one force. The F in the equation must be a constant force. This equation is only valid if the force remains constant. And as I mentioned before, we're going to rename delta T as the time of interaction. Not just a moment in time, but an elapsed time. It's how long the force is acting for. By considering the force and time as vector to scalar, we've already determined that impulse is a vector quantity. It really is a vector that points in the same direction as the force that causes it. For the units, we can build it up directly from the equation. We've got force, which you know is measured in newtons, and time, which is measured in seconds. So we just put them next to each other, and we say the impulse is measured in Newton seconds, right? You put that little multiplication dot in between them. That's the appropriate way to write it. This way it doesn't look like, like nanoseconds or something like that. So it's Newton seconds. I hope you said Newton seconds. I hope you wrote Newton seconds. I hope you certainly did not say newtons per second. Some students unfortunately say that, although there's no reason to divide them. Look at the equation. They're multiplied, right? So it's newtons times seconds. Now, the Newton second is not renamed after any famous scientist as some units are. So the Newton second is actually up for grabs. So, for example, if one of you does some, Nobel Prize winning work in impulse, you might get the Newton second named after you. And then for all future classes, I'd get to teach that new unit, and I'd say, oh, I taught that student, I'm so proud of them. Just be aware, if you ever do win a Nobel Prize, you get to make a speech in front of all sorts of important dignitaries and world leaders describing your research and why you won the Nobel Prize. And I would like to think that in that speech, you might thank me, I did get you started. And don't forget that the Nobel Prize does come with money, and I wouldn't mind that. All right, anyway, back to the physics stuff. All right, now in the equation over here, we said net impulse is sigma F delta T. So let's make that a new equation here. We'll write this as J net for net impulse equals sigma F times delta T. This is one we use when there's more than one force acting. So we're going to go ahead and box that in and define J net as net impulse. So again, this equation is when there's only one force acting, or we only care about one force, but that's very rare that that's the case when that happens. Most times we worry about the net force, and then we have to worry about the net impulse. Okay, so that was all about this left-hand side of the equation. Let's focus on the right-hand side, which now deals with momentum. And again, in class, I would ask you where you've heard of the words momentum, what has a lot of momentum. I'd ask for some examples. Maybe you want to pause the video and just think, where you've heard momentum before. Okay, so either you wrote down an idea or you had some ideas in your head. And most times students say something like a train. A train has a lot of momentum. Or maybe a bowling ball has a lot of momentum. Or a person running has a lot of momentum. The person running, that's a really good example. But for the other ones, I'd have to ask you a follow-up question. Like if you said a train has a lot of momentum, I'd have to say, well, what's the train doing? And hopefully you'd say, well, the train is moving. And for the bowling ball, I'd say, how do you know the bowling ball has a lot of momentum? What is it doing? And hopefully you say the bowling ball is rolling or moving, right? And that's the whole point, is that, the object has to be in motion for it to have momentum. Going back to the idea of a person running, the person has momentum. Sometimes carries them through to the end of a race. And oftentimes in sports, you hear about this term momentum being thrown around. Like you might be watching, a playoff game, and the announcer says, this team has a lot of momentum coming into the playoffs. Well, what does that mean? What does it mean if a team has a lot of momentum? So you might say, well, that team's on a winning streak. They'd be really difficult to beat. And well, that's a psychological thing that actually does lead us to the physics definition of momentum. So we'll define momentum as how difficult it is to stop a moving object. So again, to this idea that the object has to be in motion to have momentum. If an object is at rest, it's real easy to stop. It has zero momentum, so it has to be moving. This also sounds a little bit like inertia, right? An object at rest stays at rest. An object in motion stays in motion, except it doesn't work for the at rest part. So sometimes we call momentum inertia in motion. Now, we need a symbol to use for momentum, to use in the equations. And again, I'd ask you in class what you might want to use. And some students say m, but then I say, well, what do we use m for already? We use it for mass. That would be really confusing, considering mass is part of momentum. So we're not going to do that. And some students say capital M, but capital M and lowercase m look too much alike. So we're not going to do any of that. So again, no matter how many times I ask, unless you've seen it before, you're probably not going to guess. We're going to use lowercase p for momentum. Now, it's lowercase because remember, we used capital P before. That's for, right, power. And I know that my capital P and my lowercase p look an awful lot alike. And so right now you can see it's this sort of italicized P. But I know when I write it on the board and on papers, I write it as a lowercase script P. So I know it's not just a smaller version of uppercase P. So as long as you can tell it's lowercase, that's fine. You don't have to get all too fancy with it. All right. So for the equation that's coming directly from here is this term inside. So we'll write this as P equals mv. And we'll again define our terms here. P stands for what we call linear momentum. I say linear because there is actually another type of momentum we'll see later on in the year a little bit. And then the V in the equation is velocity. And notice it's not speed, it is velocity. If I immediately put the vector arrow above it, so I'll put the vector arrow here in the equation. Now what about mass? Is that vector or scalar? Well, we should remember that mass is scalar, and so now we see that momentum is a vector quantity. So we put the vector arrow above all the P's here, here, and here, and now we can box in our equation. Momentum equals mass times velocity. It's not about speed, it's about velocity. So direction matters, and so yes, momentum is a vector quantity. An object's momentum points in the same direction as the object's velocity. For the units, again, we can go right to the equation and build up the units from there. So we got mass measured in kilograms and velocity measured in meters per second. So you might guess the units are kilogram meters per second. That's it. Just right next to each other, plus the multiplication dot in between. Literally, that's it. As it turns out, the kilogram meter per second is also up for grabs. It's not named after anyone in particular. And so if maybe you grow up to do some Nobel Prize winning work in momentum, maybe you'll get the kilogram meter per second named after you. I'd be so proud. And then, of course, you get to make a speech and thanks and money. Right. That, of course, is the major takeaway here. Give your teacher money if you win a Nobel Prize. Okay. Let's move forward here. Going back to this word equation, we said that net impulse equals change momentum. So let's put that all together in this equation, that J net impulse equals change momentum. We can go ahead and box that in. This is the connecting equation between our terms impulse momentum. That when you combine all the forces there and extend it in time and figure out the net impulse, what that does is it tells you it's the object's change in momentum. That's what happens. So the net result of putting forces together and extending in time is the object's momentum changes. We run into a little bit of an issue, though, here, because on the left-hand side, we've got impulse, which we know is measured in Newton seconds, and the right-hand side is momentum, measured in kilogram meters per second, and we are equating the two, and these units are not the same thing, so that's not okay. Well, let's consider the Newton second for a second. Sorry. We got the Newton, and so let's remind ourselves, what's the Newton really made of? What other units makes up the Newton? So hopefully you remember, it is, of course, the kilogram meter per second squared, right? Mass times acceleration gives, net force. And so let's see what happens when we multiply a kilogram meter per second squared times a second. Well, you see one factor of seconds goes away, and we're left with a kilogram meter per second. Oh, so that tells you a Newton second is the exact same thing as a kilogram meter per second. In other words, these two units are the same, and we can equate these two terms. And so it actually means that they're interchangeable. It doesn't really matter which unit you use. It's traditional to use the Newton second when we're dealing with impulse because it says force times time. And it's more traditional to use the kilogram meter per second when using momentum because it says mass times velocity. But in the end, it really doesn't matter. They're completely interchangeable.